Hi guys, let's solve today's Leetcode problem, and it is problem number 1722. Minimize Hamming distance after swap operations. Okay, so it's a medium problem. Let's read this out. You're given two integer array, source and target, both of length n. You're also given an array allowed swap, where each allowed swap of I is a of I and b of I indicates that you are allowed to swap the elements at index a of I and index bi, zero indexed of array source. Note that you can swap elements at a specific pair of indices multiple times and in any order. Okay, so this is important thing. We'll come back to this. Now, the Hamming distance of two array of a of same length source and target is the number of position where the element are different. Formally, if the number it is the number of indices I for I in this range where source of I is not equal to target of I. Okay, so this is the condition. Return the minimum Hamming distance of source and target and after performing any number of amount of swaps operation in the array source. Okay, so just to reiterate over the question, what it says is we are given a source array, then a target array, and the allowed swaps. So what it says is the allowed swaps, what it tells basically, it says in the source array, what is the in source array, the when we have these indexes, we can swap these indexes. So these swaps are allowed. Okay, in source array. Now, after applying any number of swaps, any number of times, okay, in any order, in this allowed swaps, once we are done with all those, swaps, and we compare this source array with target, and if there is any source of I which is not equal to target of I, then that is a Hamming distance. Okay, and that is one Hamming distance. Now we have to, make the swaps such that we find the minimum Hamming distance. Okay, so we have to do the swap such that the Hamming distance should be minimum, which means the minimum difference after all the swaps, minimum difference should be there in the source and target array. Okay, so now if you see, uh, yeah, so this is the question that it says. Okay, and what we are going to cover in this video is basically union find approach that is mainly DSU, and we'll be using map for that. This is the main approach that we are going to cover. Other than that, I'll just briefly discuss the BFS approach as well. Though union find, this DSU approach is cleaner and more, standard for this kind of problem, swap based grouping problem. So we would focus more on this one in this video. Okay, now if you observe one thing clear over here, what we need to do is we need to do swaps in such a way that this need to be minimum. Okay, now just if you think, okay, one second. Yeah, if you think how you could do swap such that it remains minimum. Okay, now if let's, you know consider this example. uh, Okay, so swap need to be minimum. For example, let's dry run on this swaps. So if we see, right, if we see these two source and target array, what is the difference? So I see, I think this and this is different, this and this is different, this and all values in source and target are initially different. Now let's apply the swaps. So if I apply this one, or maybe let's see over here itself. If we apply the first swap, you see this 0 1, then our source become this. Okay, after first swap, you see this and this is matching with target, and this is still different. Now after we apply this swap, the second one, what we see is we see 2 and 1 were already same. Now when we applied this swap, you see 4 is now matching with target of 4 is, this source value is matching. Now 5 and 3 is still different. Okay, so for this, we were able to match these three values, and one value is still different. So this reason, the source of I is not equal to target of I. After applying all the allowed swaps in any order we could do, we see there is still one non-matching, value. So that's why there is one Hamming distance. And if you see carefully, there is no possible way. First is, if you see, right, in source there is this value 4, and in target this value is 5. Oh, sorry, my bad. Here, the final after swaps, you see it has value 3 and it has value 5. First thing is that they don't, there is no matching kind of a thing, right? It's not possible at all to match after applying any swaps. Let's say there might be some more, swaps which were allowed, for example. Still, we won't be able to match these two value in any case because these values itself are different, right? So that is the one thing to observe. Another thing is that after these many, swaps, uh, so yeah, this that is one thing to observe, that we when we can apply the minimum swaps. Okay, now under the other thing is, let's take this example. Okay, so this third example, if we take, so in this one, if you see, we are given this source, we are given this target, and these are the allowed swaps. Now if you see, what does this mean? That okay, I can swap 0 and 4. Okay, if I swap 0 and 4, 0 and 4, so what will happen is it will become 3, 1, 2, 4, 3, sorry, 5, and sorry, my bad. So there is no need to, apply these swaps optimally. So this can be applied in any direction, any order, but we have to think on this part, that how is this going to be impacting. Okay, now if we consider this case, that from 0, 4, 4, 2, 1, 3, 1, 4, we can go. Okay, so now if you see, if we just think, so this indexes, right, this indexes, if we just think these as a node. Okay, so indexes, if we consider these indexes as nodes, and these swaps if we consider as edges. Okay, what will happen then? These are nodes and these are edges. So what would happen? What I'm saying is that from 0 to 4 there is a node. Okay, so from 0 to 4 there is a node, and since this swap can be, both the ways, so I can say that from 4 to 0 itself there is an also there is a node. Now uh, we need to understand that from 4 to 0, 0 to 4 I can go. From 4, what I can do, I can swap 4 with 2. I can, which also means, I mean, if you see, there is a transitive property as well. What does the transitive property says? That if I can swap 4, 0 with 4 and 4 with 2, which means I can swap 0 with 2 as well. Indirectly, but I can swap, right? So this is a transitive property that is applied. So if in any case I see these three are connected. Okay, let's say if 2 is connected with 2 is not connected here with anyone else. Now we see 4 is also connected with 4. Here you see 4 is connected with 1. 4 is also connected with yeah, 4 is, sorry, my bad. 4 is connected with 1. 1 is connected with 3. Now using this transitive property itself we see, right? So 4 can be swapped with 3. Okay. Now what else we want? We want anything else? So using this transitive, or this is bidirectional, if you see. This, all these are bidirectional. So 1 can also be swapped with 4, 2, or 4, 1 can also be swapped with 2. Now in order to achieve this target, what all swaps we need? So if we see, these all values are different. Okay, source and target has all the values different. Now if we start making the swaps, so I need to move 5. Okay, what I need to do is I need to move 5 at index 1, right? So what is there in 1? 1 has this value. Here 1 has 5. So if I just swap these two value over here in source array, if I just swap, I would achieve this value, right? And using this transitive property itself, I see that if 0 can be swapped with 4, 4 can be swapped with 1, I know that these two can also be swapped. So I can simply swap these values, okay, 0 and 1. So it would become 5, sorry, after swapping 1, 5, 2, 4, 3. So I was able to swap these two values due to the transitive property that we have. Okay. Now, if you see, this is 2, 4. This value is 4, 2. And 3 is matching. So we don't need to do anything. Now we'll see that 2 and 4 already have, directly allowed swap. So we can directly swap them. So it would be 4, 2. 3 and 5 1. So in this example, if you see, we were able to match all these values are same in source and target array. So at the end, if you see, what is the Hamming distance? There is no Hamming distance. There is no differences in any of these values. So answer is 0. We don't need to actually, you know, uh, have any value which is different in source and target array at the end. So that is the kind of intuition what we are doing. Now what if you see this part that I have built, right, what it is actually. So I'm hoping you are aware of disjoint set union concept. So because I am not going to explain that in depth in this video, uh, but if you are not, you can go ahead and read about that and see what it basically says that we have in this example. Maybe let's write this example one more time. Okay, now in this example, this is source, this is target, and this is the allowed swap. So with this DSU, what it has two things. One is parent array and another is rank. Okay, so initially each node, so we have these as nodes, right, as I already told, and these are edges. Okay, now these are nodes, and you can say these are the nodes value. Okay, value. What is the parent initially? So as part of DSU, we know that parents, each node is parent of itself at the starting point. So 0 will have parent as 0, 1 has 1, 2, 3, and 4, so on. Okay, so these are parent of themselves initially. Now rank is initially 0. Okay, uh, yeah, I'll just do a dry run over here on this case. Now, yeah, so I have written the code for find parent and union by rank, these two methods. So for DSU, first is we have this initialize the parent, which is a parent, the nodes are initially parents of itself, and rank is initially 0 for all the cases. Now we start, doing union for third step is, sorry, second step is you doing union for all the nodes. Okay, nodes, edges, or whatever. Okay, for all. So now I see 0 and 4. So parent of 0 is 0, parent of 4 is 4 here if you see. Now what it says, we found the parent. Now union by rank if we see. So these are different. If u is equal to v or not, it's not. Now if rank of u is greater, no. Rank of v is greater, no. Else if parent of v is equal to parent of u. So parent of v is what? 4. So this this guy parent is 0. Okay, u, and what else? Rank of u plus plus. So this is u, rank of this is now 1. Okay, now similarly we'll do for 4 2. So for parent of 4, parent of 2, parent of 4 is 0, and parent of 2 is 2. Now if I just compare the rank, both the rank, so if you see rank of, this is my u and this is v, so rank of u is rank of 0 is greater than rank of 2. Here you see it's 1, and this one if you see it's 0. So what we will do, we will assign this parent as 0, and I'll increase the rank by one value. So this is 2. So basically, if you visually want to see what's happening is, this is one of our node 0. This was one our another node 4. What was this parent? Initially, they themselves were, parent to themselves. And when we, sort of said, okay, this would be parent for themselves. 4 is parent of this. Now for 2 and 4, what I see is, what is the parent of 4? Parent of 4 is 0. So attach 2 to 0. So we attached it. Now if we, same way, if we see, this we attached because rank was greater for 0. Now next thing is, next, 1 3 and 1 4. So 1 and 3 if we see, so 1 and 3, they have themselves as their parent, and rank is also same. So we can have, you know 1 is there and 3 is there, and 1's rank we can increase to 1. Okay, now there is 1 and 4. So 1 parent is 1, and 3 parent was also 1, and 4 parent was 0. Okay, so 4 parent is 0. So what does it says is, attach this to this parent and increment the value of this. So we increment this value here 3, and parent of 1 is 3, parent of 1 is 0, and we have increased the value, and value we would increase by 1, not just yeah, so it would be 4 now. So this is how our, uh, joint I mean, we had this disjoint set of edges. Now after doing union for all these edges, we see this is our one set of union, in which 0 is the parent for all of this. Okay, eventual parent we can say, no, if not the direct parent, so this is the eventual parent. Okay, so yeah, so we have done this pre-processing thing, that we have calculated the union. Now is, we need to check, compare uh, these two. So these are, I mean, we have calculated the union, but the thing is we need to apply this swap sort of thing, and then you do the union. So uh, what we are doing is, so we have our edges from 0 till n minus 1, right? So this is our edges. What we are doing is, we are going over these edges one by one, and we'll see what is your parent. Okay, so 0 parent will say, okay, 0 itself is my parent, and okay, if itself is your parent, then we need to map. Okay, map how? Okay, so this is one set where 0 is the parent. What all values you have? Okay, so for 0 we have all these values. 0, that is 1 time. Okay, we need to maintain time, as there can be duplicate as well. I mean, how many times this occur? Then we have 2, 3, 4. Okay, so all of this appeared only single time. So it is just 1, 1, 1 like this. Okay, though this example was such that all of this were came all together. But if you see this example, in this, if you see, this is one set, this is one another set. Okay, so it would be something like 0, 1, and then 2, 3. So how does it map would look like? That there is one set 0, which is the parent. It contains 0 one time, 1 one time. Okay, now there is another set which, all eventual parent is 2, and it has 2 one time, 3 one time. Okay, so this is how it is. And So this is how it is. So this is basically a map of int, comma, map of int, comma, int, where this is our source of I, and this is the count. Okay, I think there is one small mistake I did. So since this is source of I, right? So it cannot be 0. It is 5. Okay, that was the index. So this is my, index. That is my node, which is eventual parent. Okay. So this is how I am calculating 0, and I am basically checking for all in this all these edges. Oh, sorry, all these are my nodes. Okay, these are my nodes. I'm going through all the nodes and seeing which is the eventual parent. Okay, this is the eventual parent. Then put this in the map. So we are first, this thing we are doing is we are putting into the map. So this is my third thing. So now we have populated the source value. Okay, this is how my source, after populating this map, this is how my map looks like. Now fourth thing that I need to do is I need to find if this map contains, the target in what order I want or not. Okay, so this is my target if I have to compare. So again, we would go over all the nodes, that is from 0 to n minus 1. And after going, I would now, for this each node, I will find the parent, eventual parent. So for example, for 0, I find, okay, 0 itself is the parent. Now, when I found this, I need to check if this value 0, uh, okay, this is the eventual parent. Now in this parent, okay, I need to see if my target of I exists or not. Okay, in this set, basically the set that we have built, right, if my target exists in that set or not. So we see 0 0 0 0, right? This is my eventual parent. I was 0. I is basically node, and this target of I is, what is this target of I? It is 1. Okay, so 1 exists in map or not? So 1 do exist in map. Okay, now if it exists in map, what we can do is we can reduce its occurrence, so that next time if any other one comes, we don't count it. So we will, if exist in map, then we can reduce occurrence. Else what we can do is, if it doesn't exist, this using this eventual mapping, we have find that, okay, this node has this as an eventual parent, and if it would have ever existed, it would have existed in this set only. Since it don't exist, so as it is one of our Hamming distance, so we can increment our answer. Okay, so this is what it is. And this main key thing is that, you see this, right, this transitive dependency thing which we are discussing. Okay, if there is a node from 0 to 4, 4 to 4, how this is actually working. So for that reason, this target of I, if it exists, it would exist in this set. We have done union in such a way, otherwise it won't exist. So I need to check this in the map if exist or not. So this is my, let's say, some value. So in map I can check this value and this target of I, if this exists or not. So yeah, this is the explanation for this one question. I can now quickly write the code for this. So since we already have code for this parent union and all that, I won't write this. One is we are doing this union, so we can go over this allowed swap array that we have dot size. So we will just iterate over that, and we will do union on this, union by rank for this uh, you know source. Sorry, my bad. Allowed swap, I would just write it as swap of I comma, my bad again, I0 comma swap of I1. So I first step is done, where you see uh, yeah, this was first step, but I am hoping we already did this. So this is done. Second step is union, we are done. Third step is uh, pre-processing all the you know nodes, basically doing the union and storing them in the map such that we can compare and find the target. So second part would be in map we need to put, right? So we would have this unordered map of int comma ordered map of int comma int. This is our map. Now we can iterate over all the nodes. Our nodes come from 0 to n minus 1, and we would see if what is the parent. I can write it as parent equal to find parent source of my bad I. For this I need to find the parent. Okay, now I have this parent. What I can do is I can set group this source of I into this set. So accordingly in map I will put as mp of parent of source of I plus plus. Okay, now second thing is done. We have added this source into map based on the set that we have built. Now another thing is searching in the map for target value. So again we will iterate over all our nodes. I can be less than n. Okay, again we will find parent. What is the parent of I? We will get the parent. Now here we need to check if target of I exist in this set or not. Which set? This parent. So mp of parent and target of I, if this exists in this set or not. Okay, this is, if this exists, then we can decrement this value. Okay, so mp of parent target of I minus minus. If it doesn't exist in the map, then we can increment our answer. Here we would have our answer variable as well. And at the end, yeah, at the end we can return answer. Yeah, so that is all about it. The key thing was grouping, or putting all the nodes into the set such that it would have the minimum Hamming distance, and minimum Hamming distance would be we see the transitive property. So if there is the thing, then if there is any node in that way, we would be able to connect through that. Yeah, so now we can discuss time complexity for this approach. If you see, we are having one loop over here of n. We have one loop over here as well. Let's say this size was m, and there is this union by rank function we are calling. So this one I'll come, what is the time complexity for this, but you can say O of m into this time complexity. I'm keeping it as a box for now. Now there is this another uh, time complexity, that is O of n. And this finding parent, right? So union, we have this disjoint set union works in the way that this find parent and union by rank, it almost works in constant time. Okay, so which is basically, so time complexity for these are as you see, right, we are having we are doing all this kind of a thing, uh, which is 4 of alpha. Okay, here also it's 4 of alpha. So where of 4 of alpha is nothing but constant. Okay, now one more thing, if you see um, here, we are doing this map operation. So on an average, since we have taken unordered map, we can consider that map takes of one time complexity. So it's like time complexity is uh, this can be m, right, and then n. So O of n into alpha, I can write into alpha plus O of m into alpha. So it would be of n plus m times alpha. Okay, so this is the time complexity. And space complexity, if you see, so we are taking this unordered map, and what does this unordered map take contains is eventually all the number of nodes, right? So it would be O of n. Yeah, so this is time and space complexity for this approach. I hope you understand this. And let's just quickly, discuss. We have discussed this approach, and fine. I hope you understand that. And another is the BFS approach. So BFS is basically, here we need to, first form the adjacency list. So once the adjacency list is formed, I'll iterate over all the nodes. So adjacency list, I hope you know, like there is bidirectional, these edges that is given to us, allowed swaps. This is are the edges, which is bidirectional. So we can have this created using edges that is given to us. We need to now iterate over all nodes, and at the time, what we would do is we will have one visited array as well, in general how it is in BFS. And if it is already visited, node is already visited, we don't need to visit it. If not visited, we can have a queue data structure, and then we can traverse all the adjacents for that queue. So once that adjacent is visited, so what we would do is we would basically form a component. Okay, so since with adjacency list I know what all neighbors are there for a particular node, so I would visit all its adjacents, and I would make component from that node. Okay, and once this component is formed, I would, this is component, and once this component is formed, I would go over this array, and I would uh, we would have this map where I can, put this component. So one is in the map I can put using some source value and so, and then in a map I can find for target values. And if it exists, this is we can, accordingly reduce the its count in map, and if it doesn't exist, we can have our answer incremented. So this is how we can do BFS for this, but it's not very clean, so I'm not going to do that. But I hope you understand both of this approach. I would attach code link as well for this BFS approach, but this is the cleanest approach for this, which is recommended as well. That's all for this problem. I'll add GitHub link for my code in description below. Thank you for watching. Stay tuned for next video. Bye.